Monster Scale Summit. I'm Rachel Stevens. I'm the research director at RedMonk, where we track technology adoption trends as seen through the lens of the practitioner and the developer. Basically, we care about the experiences of the people who are writing and running software and the people who have their hands on the keyboards. People like you. I'm delighted to be here today. And in just a few minutes, I'm going to be joined by Adam Jacob, and we're going to talk about building technology at scale. But first, I have to make a slight confession. I dropped every philosophy class that I registered for in college. I had no patience for the thought experiments. And yet here I am about to open this talk with a very cliche thought experiment. And I hope you will forgive me because you've probably heard it before. If a tree falls in the wood and no one hears it, does it make a sound? I think, for the record, my answer is yes. And I would also like to remind you that Albert Einstein's response to this thought experiment was, do you really believe that the moon only exists if you look at it? So when I move this metaphor forward to the next slide, please just keep those answers in your heart and maybe try not to yell at me on social media, please. But our metaphor is going to move forward right now. Does your software exist if your users can't run it? You're probably right now having an initial reaction that's akin to an eye roll, thinking I'm a talking head who doesn't know what they're talking about. I'm not here to say that your work is for naught if your database has fallen over, although if that is happening to you a lot, maybe you should look at ScyllaDB. Believe me, I started my career as a DBA. I know that feeling in the pit of your stomach when you drop a production database. I know that it can be really thankless work to run even a small system. And so hearing someone on screen implying that your work doesn't exist is probably very irritating. And you're probably out there thinking, of course the code is still living in GitHub even if US East 1 has gone down. Or just because there's an outage somewhere in your stack doesn't mean that your entire application has poof, disappeared from existence. But just humor me for just a minute. Let's play with this thought experiment just a little. A lot of the times when we're talking about scale, we're talking about the throughput and traffic scale. If your systems are perpetually falling over and your servers can't handle the load over and over again, if your users know they will not be able to reach you or rely on being able to connect with you, they know that they can't interact with you on a consistent basis and that your application is not really there for them. Does your software truly exist to your users? That's traffic scale. If your integrations break every time an API changes and your dependencies are just this twisted web of fragile connections and cascading version failures, does your software really exist in a reliable and stable form for your users and your partners? That's an ecosystem scale question. If your software can't handle different languages, offline use cases, low connectivity environments, if it ignores the realities of mobility, timeouts, regional constraints, is it there for a global audience? A lot of the times we're thinking about geographic scale in terms of distributed systems. But have we thought about the personal and user side of what it means to scale geographically? If your architecture is built in a way that is too expensive to run and sustain at scale, and if the cost of growth exceeds the value that you're delivering, does any of this matter anyways? That's economic scale. Software at scale isn't just about throughput. It's about making sure that your code endures, adapts, and remains accessible no matter the load and location of where you're running. Because if your users can't use it, your software may as well not exist. And that's why we're here today. We want our software to be real for our users. We want to learn from each other about how to build performant applications at scale that matter. And also, encountering problems of scale is fun. As Adam Jacob is about to tell you, it is the funnest game. It's also frustrating, and it's beautiful. We get to build these amazing and complex and magnificent systems. Frustrating because at scale, things tend to fail in surprising and very unpredictable ways. And beautiful because it means that when you're building at scale, it means that you're building things that people care about, things that people are using. And building at scale is not a guaranteed problem that we all get to have. There are so many problems projects out there in the world that never get to have this problem. Should we all be so lucky to be getting to solve these problems? And so without further ado, one of the people I enjoy most in this industry is Adam Jacob, and he solved these scale problems as a co-founder at Chef. He is now a co-founder CEO at a startup called System Initiative. And for the remainder of the session, Adam is going to be talking with me in a Q&A session, sharing his wisdom about building at scale. Thanks. Hey, Monster Scale Summit. I'm Rachel Stevens, and I'm here with the one and only Adam Jacob, and we are here to talk about the many challenges of scale in all of its forms. And so, Adam, as someone who has built a project in the past, built a company, all of these wonderful things, I think you've been around the industry long enough that you have seen architectural patterns come and go. You've seen ones that stay, that comes and goes, ebbs and flows of the industry. Talk to us. What have you seen in terms of patterns over the course of your career?
Oh, I mean, there's so many. The stickiest one, though, is that in the end, you're using computers to deploy applications, and then you stick them on networks, and then they serve stuff to the internet behind load balancers. And, as reductive as that sounds, when they talk to databases, sorry. And as reductive as that sounds, a lot of the architectural things that have come and gone over the years are really just attempts to make that somehow simpler or more straightforward or whatever, more industrialized, easier on the developer. But in the end, the stickiest pattern, especially when you think about or reach scale, always returns to, and how efficiently can I run a bunch of computers with the application I want to run that talks to some large database to store information. And then, whatever, we move it around, we change the shape of those things, we move some of those variables, but that's the architectural pattern that sticks, which is load balancers, compute, some kind of database.
Fair enough. Well, I feel like that makes it sound like it's, nice, straightforward. I think a lot of us here have realized that it can be anything but, especially when you're starting to get into these high scale distributed applications.
Yeah.
Yeah. I think let's talk then about some of the lessons we have learned along the way about the challenges of scale. Because I think we're in a world where we're building complex things, we are moving fast, and we're trying to make decisions with imperfect information. And I think one of the challenges that we can come up against a lot of the times is that our intentions are to build things well. We want to not we don't want to slap things together, but we also don't want to optimize too soon. So let's talk about just thinking about just that spectrum to start with. How do you think about that?
Yeah. I mean, I think of it basically through the lens of optionality. So, okay. When you start building new things, it's nice to not worry too much about scale because you may never reach it. And most of what's in the way of when products fail, it's usually not because they failed to scale. Think about how badly Twitter failed to scale, and yet here we are, So your ability to survive a failure to scale is higher than I think most people realize if the product is great and it sort of has great product market fit. I think the pieces that you do look at though tend to be architectural over time. So, back to sort of your first question, what are the sticky architecture patterns? We know that the reason that compute behind load balancers is so sticky at scale is because it scales well. Because if you just think about it as I have a bunch of relatively stateless application servers that sit behind a thing that routes them traffic. And we learned 30 years ago that the dumber the load balancer, the better under load, and that was after spending tons of money trying to figure out how to do more complex load balancing algorithms. And so usually as we get bigger and more scalable, what you tend to start to see are a reduction in the number of different parts that are in the system to some degree, and then more clear architecture boundaries between them. So, you start to see things like more queues, right? And more message buses and more load balancers, more compute. And that's because when you're thinking about how to scale the system in the initial case, you're can I build a product that is good? It's easier to build that product that is good by just sort of using whatever I have, because the question is, will anybody care? And then once it becomes not a question of whether people will care, and it becomes a question now of how do I scale the technology, now it starts to become a question of, great, what are the pieces that I've chosen in order to make this first version of the product work at all? And how do I sort of move through each of those things kind of in a theory of constraintsy sort of way, where it's like, okay, here's the bottleneck. How do we move that bottleneck? And how do we move this bottleneck? And frequently that process is one of sort of refactoring the architecture itself, of saying, hey, we started with this architecture, but it doesn't work at scale, or won't work at the scale we need it to work at that we can already predict. And then, it becomes this process of refactoring. I think the idea of like premature optimization is an interesting one, because like for sure it's real. And at the same time, if you're 20 years into your career, or 15, 10, doesn't matter, if you've been around the block a little, there's some decisions you would make in the beginning that, because that if it works, you're going to be happier with your life, and
Okay.
And, those are things like thinking about factoring the code in a way that allows you to break it apart across network boundaries over time if you had to, right? Where like, you might not do that if you're like year 2 of a software developer, you would just keep writing code sort of all in the same spot or all in the same way. And you wouldn't really think about how those boundaries like layer together. And so it becomes a question about like, how do you write the code initially so that when you think about its boundaries, maybe it's all running in one process now, but if I had to refactor it so that it was running in 2 processes later, or it was running on a network later, how do we do that?
Do you have any scaling horror stories that you want to share from your chef days?
Oh, I have not just from Chef. I have so many. The funnest one probably was, this is a good example of premature optimization. So we launched this SaaS service. We were getting ready to launch the first version of Hosted Chef. And so it was this configuration management service you could sign up for, and then you could, manage all your compute with Chef. And the problem we discovered the day before we launched was that it took a minute and a half or so to create a new user. Like, just the way that we had structured it meant that like the number of things it needed to do was just going to take forever. And we had literally never tried. It didn't take that long when you were just running the thing on your laptop, but it took a very long time later. And we never tested it. We just assumed it would be easy, and it was not. And so, in the last hours before we launched this service, we moved it from anyone can sign up and just get an account to now you're in like a queue. And we had someone's partner draw like a little cute space robot. And we were like, hey, the space robots will get back to you. Demand is so high, we could never possibly, it just sort of papered over the scalability problem.
Love it.
Similarly, another example here was that same Chef server that like couldn't create an account very fast and that didn't scale very well that we launched the SaaS service with eventually had to work at Facebook. And, the architecture that we had originally, which was Rails. So the Chef server was basically written in Ruby and was great to work with. But what we needed was like a much higher degree of parallelism inside the system because, at the scale of Facebook, you were going to have 40 or 50,000 things, perhaps all at once, sort of pointed at one direct Chef server. And so we rebuilt it in Erlang, which is great for that sort of problem. And, it was one of the most incredible experiences of my life because I basically brought that Erlang version of the Chef server on a USB stick to Facebook, and we like plugged it in and installed the new Chef server, and we replaced the old one. And then we bootstrapped a whole data center on top of it. And we thought that it was broken because the load didn't move, right? Basically, we were using less resources at idle to bootstrap that data center. And it happened in almost no time at all. That before, like, just couldn't even work over the course of days. And it was incredible. And like, I don't think you could have predicted if in order to get Chef into the world, what we had done was written the Chef server in Erlang. I don't think anybody would have cared about Chef. I think we'd have died there, but because we did actually know what the system was, we knew what it needed to do. Like that mechanism of saying, well, architecturally, we can change it so that this architecture looks different. Part of it's the language, part of it's the runtime. And now we can solve this problem at much bigger scale.
The Rails thing is great because it allows us to care about kind of mass adoption, and we can get to a place where lots of people can use this. But Erlang lets us get to a place where we can solve kind of niche problems or more fine-grained problems.
Sure.
Like, how do you kind of get to a place where you make those trade-offs, and at what point do you decide to kind of make that, like, pull the duct tape off and switch things over? Like, how
Yeah.
did you think about that?
I mean, it's when that becomes the thing that's standing in your way,
Mhm.
you know? And, for Chef, that what was standing in our way of getting that customer was it didn't scale. And so you had to think, how am I going to solve this problem in a way that scales to the size of their problem, which is, humongous. And so, do you want that or don't you? And there's not that big of a difference in some ways between like Facebook and, JP Morgan Chase, right? They operate very differently, but in terms of their scale, it's the same. So like for us as a business, we wanted both of those targets, I wanted both of those people to pay me money. Neither were going to do it if the system didn't scale to the size of their needs, right? And so making it scale to Facebook meant that we obviously would scale to whatever we needed to do. And it worked. But it was not a small amount of investment, And I think, this comes back to the question of like, how many like, there's this concept of like innovation tokens and what places do you innovate and where do you buy and where don't you, and those sorts of questions. And I think the core of what you do, you just can never, you can never buy it. Like if it matters to the customer, if it matters to the experience, if it matters in that way, like you have to build it yourself. And sometimes what you build doesn't fit, and you have to be, the sooner that you recognize that it won't fit and then do whatever you have to do to make it fit, the better. And a mistake people tend to make is they wait too long to realize that what they have is a deep architecture problem and a business problem that says, if I don't scale to this size, I will die. And therefore they just, because addressing architecture problems takes longer than just like writing a feature. You know what I mean? Like if it's going to take you 6 or 8 months to figure out how to rebuild this system so that it scales the way you need it to scale, like you better start that problem, in advance of when you need it done, because it's probably too late.
I think a lot of us want to talk about the building process and the technical specifications and all of the things that we're doing that is really cool on the tech side. And it can be a little gauche to talk about like the application cost and the ROI and the TCO and like all the MBA speak kind of things cannot be very fun. I think one of the parts of scale that matters a lot, and we just don't always name it, is the cost of what it costs, like the cost of scaling something tends to be an impetus of things. So, yeah.
I mean, I think you have to understand the game that you're trying to play. And, so like, let's say you're playing the venture capital game. So what you've done is, you've got some software you've built. Your goal is to turn it into a big company. You want to go public. You're going to make everybody billions of dollars. Your goal is billions of dollars of annually recurring revenue, right? That's very hard to achieve, right? A lot of companies that people think are at that level are nowhere close, right? Getting anywhere close to 100 million is a real achievement, right? Very rare. Getting to 500 million, even more rare, like it just gets rarer and rarer sort of as you go. So that question of like, what game am I playing is really important, because in the case of like venture capital, often the game you're playing is the one that says, I need lots of customers, I need lots of traction. I do care about revenue. And so, if I can, in the ideal case, I have revenue that aligns to the customer base that I'm getting, and I can show sort of how efficiently I get them. And in that storyline where you're living on other people's money, but it's okay because you're growing at a rate that says that later on you can become scalable in terms of spend, like that's a good trade to make. And as engineers, knowing that that's the game you're playing means that you can spend your time focused on the parts that maybe will break at scale, but you're willing to spend money in order to scale in ways that you wouldn't actually want to do if you were balancing it like your home budget. Do you know what I mean? Like it just doesn't make sense to do, but you can like literally throw money at it sometimes, and that's great. There's a flip of that, which is if the game you're playing isn't that game, if the game you're playing is how do I generate a profit every month, right? How do I make sure that we don't lose money? How do I show, bottom line efficiency? If that's the game we're playing, suddenly it starts to matter a whole lot that you're overspending on database deployments, or you're overspending, your architecture sucks, or you chose a programming language that doesn't scale very well. And like suddenly those things start to really, really matter, because in the case where what I have to do is show a profit, right? Then suddenly those choices really impact me, right? So as an engineer, if you know what game you're playing, you can actually make scale decisions that have a hugely material impact on the shape of the business, right? But you have to know which game it is. Like, am I playing the game that says I'm growing and I can spend money and it doesn't matter? Or am I playing the game where my efficiency matters the most, because that's the way that we're thinking about how what we do is valuable, or how it puts, money in the table. That thread between the software architecture and the rest of the alignment, like, that's a meaningful thread of scale. It's the thing that drives a lot of our decisions.
It's intrinsically tied.
Yeah.
I want to close out on like the scale of people. So I think one of the things that I love in some of your just kind of Twitter posts from years gone by is your anecdotes of people coming up and telling you that they hate Chef, which I'm sorry.
Don't be.
But like when you put software out into the world, and when you put your art out into the world, basically, and it becomes not yours anymore, it becomes like the property of everyone who has used it. And so like when your scale has worked sufficiently, it has it goes out into the world, and some people surprise us, and people are people, and it's messy. So I want to just wrap with the wisdom of like, when your tech has scaled and your art has gone out into the world, and people then have strong opinions about your art and the software that you wrote. Like, what is your wisdom for people? Like when your software has scaled, what is your wisdom for that?
Yeah. I mean, you got to think about it as it's very hard to build things that people care about. Like, it's just rare. And so if you are so lucky as to figure out how to build something that you love, and that then you give that to the world, either because you sold it to them or because it was open source or whatever the mechanism was, and they love it back, that is so rewarding. Like, it's such a valuable thing that happens, and inevitably someone won't love it. And I think the way to think about it is really just that when they don't love it, it's also a gift, because like they're probably right about whatever their experience was, like they're probably wrong about the solution. They'll be like, you should have just done something obvious and simple. And you're like, yeah, that's because you don't understand the problem. But it doesn't matter, because ultimately it's still a compliment in its own way. Like, I had someone come up to me in a coffee shop, and like, I was wearing headphones, and they knocked on my shoulder, and they were like, "Are you Adam Jacob?" And I was like, "Yes." And they're like, "You wrote Chef?" And I was like, "Yes." And they were like, I hate Chef. And, like, I was like, "I'm sorry. I didn't write it to hurt you." But at scale, part of what that meant was that he'd used Chef. Like, he'd had that experience in his life. It had happened for him. And like, what more could you want if your goal was to get a lot of people to experience what it is that you want to build or what you think is great? And I think you can just sort of learn to let it go, because nobody's going to like it. Not everybody's going to like it. And it's not really the reason why we build this kind of stuff at scale anyway. Like, not for me. Like, I build this I love the technology of it. I like the problem. I like the difficulty of the space. And when you can then layer in more and more layers of scale in terms of like people using it and business scale, like you're just adding more and more layers of complexity to that scaling problem. And that's the funnest game. Like,
yes,
like there is no funner game than the at scale technology game for me.
I love
like,
this.
So fun. But if you're going to play that game, people will hate you for it. Some number of people will hate you. And it's okay. Because that's the game you decided to play.
I think that was the perfect wrap about technology at scale, and you layer in the business side, and you layer in the people side and the human side, and it becomes a beautiful game.
It's the funnest game.
Funnest game. Adam, thank you so much for your time today.
Yeah, my pleasure.